In this segment, we're going to talk about performance and cost model sensitivities. Now, traditional sensitivity analysis is looking at the impact of your assumptions on your outcome observations. There are at least two categories of assumptions we're going to want to look at. This includes looking at fixed parameter values as well as mathematical formulations. This could take the effect of looking at variations in those assumptions to see the impact on the outcome parameters. Additionally, we may want to conduct variations on our inputs to see the smoothness of our output spaces. In this particular case, we could look at local perturbations around point designs to see if our insights are stable to variations in how we sampled or enumerated the design space. Within our models, we can also look at the impact of variations to our constants. Lastly, we may want to look at the sensitivity of our choice of model itself and the impact of that on our insights. Now we're going to talk about two examples of these types of sensitivity analyses. First, let's look at parametric uncertainty to a satellite system whose mission was to measure the neutral atmospheric density. The purpose of this was to improve our atmospheric drag models. We can start off by constructing a tree diagram to identify a key source of uncertainty. Here, we decompose from utility to attributes to intermediate variables that need to be calculated. In this particular case, we trace it down to our leaf nodes where we had to make assumptions of values. In this particular case, we're going to look at the impact of atmospheric density and satellite density. For the sensitivity analysis, we're going to select relevant designs in order to trace the impact of variations in our assumptions on those designs. This is for illustration purposes. One could look at a larger set if one desires. For this particular case, we look at the trade space and the Pareto front. We pick three distinct categories of designs. One's a low altitude, short lifetime, one's a mid altitude, mid lifetime, and one is a high altitude, high lifetime. Next, we look at the impact of variations along the nominal value we had chosen for satellite density. We can see here the plotted curves of utility and cost versus our assumption in satellite density. In this particular case, across these three designs, they're quite insensitive across the range. The most sensitivity appears to be at the lower end of satellite density. One key takeaway from this is that we can see that all designs are not equally sensitive to our assumption. Next, we can look at the impact of atmospheric density. Now, in the real world, we know there's going to be variation in atmospheric density due to the solar cycle. However, in our model, we assumed a fixed atmospheric density. We want to check the sensitivity of our insights to the assumption of a fixed level. What we're going to do is we're going to vary the atmospheric density from its mean level to its min and max level that's expected across a solar cycle. Here we can see the impact of variations in atmospheric density at solar min, mean, and max. In particular, we can see that the impact of the atmospheric density is nonlinear and strongly affects the designs differently. In particular, the lower altitude designs are strongly impacted by the atmospheric density. Now, since we see that the sensitivity here can have large impacts on the value of each alternative, if the density value itself is actually uncertain, we may want to pursue an adaptable design. In this particular case, the purpose of the mission was to measure atmospheric density, so we know, in fact, that it's uncertain. This leads to a large risk in our system selection. Since our solutions were sensitive to the value of the density, we wanted to come up with a new solution that would be able to take advantage of information as it revealed itself over the course of the mission. In this way, sensitivity analysis can give us insights into new creative design alternatives. Now, the next example, we're going to look at the impact of model choice. Returning to the space tug system, the original evaluative models were quite straightforward. However, we did make arbitrary decisions on the fidelity of those models. One could change the fidelity, both in terms of the representation of the design, for example, adding additional design variables to represent aspects of the design, and in terms of the evaluative model itself. We could have, for example, a higher fidelity speed model to determine the response time for different alternative space tugs. In this particular study, we looked at 4 different evaluative models. The first was our baseline space tug study. In this case, the yield was 21%. That is, 21% of the trade space was deemed feasible based on our expectations for utility and cost. There were 10 Pareto efficient designs. Next, we decided to improve the fidelity of our response model. Instead of a binary model, we used a mathematical relationship to predict the speed of alternative space tug vehicles. In this case, the yield again was 21%, and there were 9 Pareto efficient designs. In the next model, we added the design variable material in order to recognize the impact of advanced materials in our design choice. This required updates to our evaluative models to take into account the impact of the new material. In this particular case, we allowed the space tug to either be made of aluminum or carbon. The trade space here had a yield of 23%, with 15 Pareto efficient designs. And lastly, we combined the improved speed model and the improved fidelity and representation, that is, the material design variable, into a combined evaluative model. In this particular case, the yield was 23% and there were 16 Pareto efficient designs. So the question is, do patterns of decisions change across these different evaluative models? In this particular case, we can inspect the Pareto front of the baseline model versus the combined model. What we see here is that our insights at the low-cost region are not sensitive. The same Pareto-efficient designs appear. In the mid-cost region of the trade space, we see that Model 4, the combined model, starts to favor electric vehicles over nuclear. And then in the high-cost region, the baseline model expected nuclear vehicles to be high value, whereas the combined model, the higher fidelity models, predicted large electric vehicles to be dominant. What we see here is that evaluative model choice does have an impact on our ultimate insights. It's not always obvious which particular evaluative model should be used. Looking across evaluative models, one might be able to get more stable insights that are less sensitive to model choice. In particular, sensitivity analysis should be conducted at different levels, everything from variations in parameters, variations in inputs, to model choice itself, in order to get confidence in fit for purpose for evaluative models for trade space studies.